Hello, this is my Lab 1 presentation. My name is Hannah Day, and this is for Physics 2211 with the Summer Soup section. The object of this lab was to create a video and construct a code that showed an object moving at a constant speed that did not change direction. This is an example of velocity, which takes into account magnitude and direction. So in order to have a constant velocity, you have to be moving at the same speed, which would be the magnitude portion of the velocity vector, and at the same direction. And this is a reflection of a few fundamental laws of physics, which include Newton's first law, which the textbook states is that every body persists in a state of rest or of moving with constant speed in a constant direction, except to the extent that it is compelled to change that state by forces acting on it. In other words, an object in motion stays in motion unless another force acts on it. And then Newton's second law is also the momentum principle, which is delta P equals F net times delta T, where a net force causes the momentum to change. A net force is the sum of all forces acting on an object, so unless F net is 0, the object's motion will change. So in this lab, we aim to have the F net be 0 to keep that velocity constant. This is a video that I was analyzing for this. So just really short, tennis ball moving across a flat concrete patio. The tracker analysis is pictured here. I went through and plotted the motion of the ball along the patio, and tracker made this graph and this table for further analysis. This is some of the GlowScript code that I used. I did use the starter code as a base, seeing as how I have no prior Python experience. The lab ran a simulation with a ball and a track model, and it gave a file of time and position points to use in the analysis. This is the picture of the motion. The ball started at this yellow dot and moved to the side at a constant velocity as shown in this position versus time graph that it gave. This code was included to have a net force of 0, which is what accounts for this completely straight line moving through the position versus time graph. This did not take into account any other forces acting on the ball. Graphical analysis of the experimental versus expected position of the ball. Experimental is the blue line, expected is the gray line. The expected is definitely straighter and more precise, and the experimental, though, is not too far off of the expected, so the idea of the experiment is in fact conveyed in this graph, where a constant velocity is that straight slope moving to the upper right hand corner of the graph. The lab asked what if you were to flip the axes. So in this lab we decided that the x-axis was the time and y-axis was position, which is typical of science. But then if you flipped these, what would the graph look like? So the graph on the left is the one with time on the x-axis, and then the one on the right is the graph with position on the x-axis. If this experiment was perfect, the line would be completely straight and therefore look the same both ways. But because there was a little bit of fluctuance in the force at the beginning here, as you can see on the left graph with that time versus position, it started moving a little slower and then picked up. The graph is a little different when it's flipped, but essentially they are the same kind of graph. And then what does it mean? The net force was in fact 0 in the computational model. That is a line of the code in GlowScript. So this assumes that there were no other forces acting on the ball, but really there were. So other contributing forces could have been the initial push of my hand on the ball, the friction between the patio and the ball, air resistance, because this was not in a vacuum, and then wind, just additional forces in the air besides just like the regular resistance. So I would say you cannot tag a definitive number of forces acting on the ball, but we do know in fact that there were other forces, and that accounts for the slight fluctuance in the graphs for this lab. Thank you so much.